In this video, we're going to talk about cryptography. The basic setup is that you have two people, say Alice and Bob, and Alice wants to send a message to Bob. So we're going to send a message from A to B, and there's a possibility of an evil adversary intercepting the messages in the middle, so generally called Eve or Oscar. And there's basically two branches of cryptography. There's private key encryption and public key encryption. And the idea with private key encryption is that the two groups meet ahead of time. They decide on how the data is going to be encrypted, and then they go apart. They go their separate ways. And then since they met ahead of time, they know how the data is going to be encrypted and decrypted, and then they can talk back and forth that way. The problem with that is that it's still possible for people to intercept the messages in the meantime. And you also have to trust each other. So Alice and Bob would have to trust that they're not sharing this method, or they're not leaving the encryption or decryption keys, lying face up in their office or whatever. So you really need to be trusting if you're going to do this. And this is called private key encryption. The fact that you can actually do public key encryption and that it's safe is surprising. So we'll talk about that in just a few minutes. Really, just a few keywords before we start. The message that Alice is trying to send to Bob is called the plain text. The message that Bob actually receives from Alice that's already been encrypted is called the ciphertext. And then he uses the key, which always refers to the method that you're using to encrypt and then decrypt the data. And so Bob will take the ciphertext, apply the key, or what I mean by that is since he knows the key, he can undo the key, and then he can arrive back at the plain text that Alice sent to Bob. So that's the basic idea. What we're really going to do is we're going to take the English alphabet, which has 26 letters, and we're going to write each of the letters as a number 0 through 25. The reason for doing this is that what we're really doing is we're working over the ring of integers mod 26, and then all addition and multiplication is done mod 26, and you stay in the ring and everything is nice. So this is private key encryption. And again, I have lots of details in this handout. This is really just some notes from the lecture notes that I have online that I'm using here. The first and most obvious way that you can encrypt the data is with what's called a substitution cipher. And that's you go through and you look at all these. So you write down something like Christmas is coming. And what you would do is you would take each of the letters, and then maybe you would add 5 to all of them. So Christmas would be, instead of CH, it would go, so Christmas would be CHR. So if you add 5 to each of these, it would be, your C's would become H's. Your H's would become M's because we're adding 5 to each value. Your R's would be 1, 2, 3, 4 W's. Okay, so this is a substitution cipher. So all the C's get turned into H's, all the D's get turned into I's, and so on. So you'd just be adding 5 to each value. And then if that's how the data is going to be encrypted, to decrypt it is super simple. You just take each of the values that you get. So you would get some jumbled up mess of letters. You would turn it back into numbers. You would subtract, say 5 or whatever the value is that you decide ahead of time. You would take that value and subtract that from each of the numbers, and then you would recover your plain text. So that's what's called a shift cipher. And so really what you're doing is you're working over the integers mod 26, and you're applying this function, f of x is x plus k. To decode, you would just apply the function g of x is x minus k. That turns out to be the inverse function, and then you can arrive back at the plain text. One step up from that, really not much fancier, is called an affine cipher. Affine is kind of, if you've ever taken a linear algebra class, you know that when we say something is linear, what that means is that it has kind of a flat shape to it. I'm being very generic, so like a line or a plane, and it goes through the origin. Affine refers to, it still has that flatness, but maybe it doesn't go through that plane. So something like ax plus b is affine, so something like a line. So that's what an affine cipher is instead of thinking about the function x plus b, you would look at ax plus b. And so here, if you want this to be reversible, if you want this function to have an inverse, you can't multiply by any value alpha. For example, you can't multiply by 0 because 0 doesn't have an inverse mod 26. And of course, as we know, to have an inverse mod 26 means that you're relatively prime with 26. And it turns out that there's 12 of those values. So this is called the affine cipher. And then to undo this, if your code is AX plus B, to undo it, you would subtract B and then multiply by alpha inverse. And then that's how you would undo the code. And that would turn the ciphertext back into the plain text. So to decrypt. So those are shift and affine ciphers. In the notes, I have substitution ciphers, and I'll let you look at that. So there's the Vigenère cipher, which is basically just a fancy substitution cipher, except here what you do is you pick a keyword. In this case, I picked vector. You write down what each of the numbers are corresponding to the word vector, and then you shift the first letter by 21, the second letter by 4, the third letter by 2, and so on, the sixth letter by 17, the seventh letter by 21 again, the eighth letter by 4, the ninth letter by 2, and so on. Okay, so that's the idea. The way that these ciphers fail is that they're all substitution ciphers, and that basically any E in the plain text gets translated to a particular letter in the ciphertext. So it's most commonly one letter that's used over and over. So this is particularly the case for shift and affine ciphers. If all your E's turn into H's, and if E is the most common letter in the English language, then H will be your most common letter in the ciphertext. And so you can kind of go backwards that way. And they have what are called frequency attacks. The substitution cipher is a little bit more sophisticated than the shift or affine cipher even, but it's still susceptible to these frequency attacks. And there's different methods that you can use to figure out the length of the keyword. And then once you know the length of the keyword, then it's not so hard to figure out that you only pay attention. Like if you know that the keyword is 6 digits long, then what you can do is you can just pull out every sixth character from the ciphertext, and then now that's basically just a plain old substitution cipher, and you can go from there. So that's the Vigenère cipher. Actual ciphers used in World War I were the Playfair cipher, which was used by the British, and then Germany had its own. This is kind of, it looks like a matrix almost, but Germany had its own similar cipher that was used. And I will leave the details to you here, but the idea is that you pick a keyword, you delete all the letters that are in the word more than once. So in this case, if our keyword is remainder, then we would get rid of the E and the R because we already have an E and the R earlier. And then you write down the first kind of distinct letters in the word. You write down the rest of the alphabet, and then you can use this pattern to encode and decode the data. And the way that this works is that you're going to take some code, say meet at the schoolhouse, break it up into 2-character chunks. And then if you have a chunk like this, so here you have 2 O's next to each other, what you need to do is you need to avoid that. So if you have the same letter repeated in the same chunk, this method isn't going to work. So what you have to do is you have to insert an X or insert some other letter. And then if we insert an X here, you have to kind of regroup the rest of the data. And then we're going to add an X at the end so that we have pairs all the way down. And then to encrypt the data, what you're going to do is you're going to look at this block of letters here. So if you wanted to say meet at the schoolhouse, the first chunk of data you would have would be ME. It's in the same row. And so to encrypt the data, what you would do is you would take these letters and move them one space to the right. So ME would become AM, and then that's how you would write down this first chunk. And then ET, let's see, ET, those are in different rows and columns. And so, ET would become AQ, because ET, what you do is you take the row of the first one and the row of the second one. So if you look at E and T here, then you look at the value that's in this row and this column, which is A, and then the value that's in this row and this column, which is Q. So you get AQ, and then this process is completely reversible. Everything is straightforward, and there you go. The Germans had a different method, but it was basically the same level of sophistication. And the idea is that this is called the ADFGX cipher because A, D, F, G, and X are all very distinct letters in Morse code. And that's how this code was translated to and from, is using Morse code. And so the idea here is that you're going to take the 26 letters in the alphabet, you treat A and I the same. I should have mentioned that you did that before too. So if there was a J in our word, we would have deleted it because we already had an I. So you treat the I and J the same. And then once you have, so for the Germans, they just had a 5x5 array of letters. They can be whatever. You pick a keyword. In this case, we picked Roman. And what you do is, so let's say you wanted to send the same code, meet at the schoolhouse. You would take ME, so M would translate into, I'm sorry, I have a different code here. So if you wanted to do meet at the schoolhouse, what you would do is you would take this letter M here in this column, and you would change it into a GA. And then you would basically take a keyword. In this case, I might as well just work with the code Julius Caesar because that's going to be easiest to look at. So your J, which is an I, is in the G row and G column. Your U is in the X row and D column and so on. So you can write down, so each of these really is just a substitution cipher so far. And then you take a keyword, you write down these letters that you had, so G, G, X, D, F, D, G, G, X, D. And then with the keyword, you put the letters of the keyword in alphabetical order. That reorders the columns, and then you can send off that code. And if you know the keyword ahead of time, then you can undo this process. This is time intensive. This took a lot of energy to do, but this is how messages were actually encrypted in World War I. And you really need to know this 5x5 array. You need to know the keyword, and then it's kind of a time intensive process. Okay, that's why people were paid money to be cryptographers in World War I. Okay, so that's how that works. I have other methods here. I should actually mention that in practice, what actually happened for the Germans in World War I is they did not use this cipher, the ADFGX cipher. What they ended up using was the ADFGVX cipher. They added a V, and that made it possible to have a 6x6 array. And then what you could do is you could have all 26 letters and the 10 numbers, which turned out to be very useful to be able to have the numbers in there as well. And then basically it was as before. So you would come up with a 6x6 array, and then you pick a keyword, apply this process. This is completely reversible and everything is fine. Okay. A little bit more surprising is the existence of public key cryptography. So the fact that Alice and Bob can send a message to each other without having to meet ahead of time is a little bit tricky. But the way I like to think about it, and I have it written here, so this is a non-mathematical way to think about it, is that if Alice wants to send Bob a secure message, the way that she does it is she takes a lockbox, and it's a lockbox. It's a special one that you can put 2 locks on it. And the way that it works is that she puts her own lock on the lockbox. So she writes her message. She puts her own lock on the lockbox. Only she can unlock it. And then she sends it to Bob. Now, Bob gets Alice's lockbox with Alice's lock on it. And what he does is he puts his own lock on it and sends it back to Alice. So Alice gets from Bob her lockbox that she sent originally with 2 locks on it, the one from Alice and the one from Bob. And then Alice can undo her own lock and take her padlock off. And now Alice has her lockbox with her message inside with Bob's lock on the outside, and she can send that back to Bob, and Bob can unlock it because he has the key. It's his lock. And so then that way Alice can send to Bob that message. And in this way, it's kind of something that is completely transparent and completely open all the steps of the way, and yet it's still secure. Just kind of this quirk of number theory here. So the first people to describe this algorithm were computer scientists Ravesh Shamir and Adelman. So this is called the RSA algorithm. And RSA is still something that's it's not exactly used this way, but these ideas have been adapted, and adapted ideas are what still is implemented even now. So they have kind of slight levels of sophistication up from the RSA algorithm, but the RSA is the easiest mathematically to describe. There's some technical reasons why RSAs, basically, if you think about the process of sending the lockbox to and from Alice and Bob, it takes some time and it takes some money. You have to ship, you have to basically ship this thing 4 times instead of once, right? Or 3 times rather, but you have to ship it more than once. And so this costs lots of money for actual implementation. And so in practice, what ends up happening is that you get this algorithm, and in order to talk back and forth, oftentimes what gets encrypted is a private key encryption. So you can actually encrypt a private key encryption using a public key encryption, if that makes sense.